Okay, hello everybody. Welcome back. As usual, there's some technological weirdness going on, and so I can't show the computer, so we're gonna do it on paper. It's gonna be ridiculous, but we're gonna do it on paper, and we'll see how the thing goes. Yeah. Will it record it? We will. Actually, let's see if we can. Okay, so at least we'll get a recording of it, hopefully. Okay, so here we are. We're back again. We're got through most of the infrastructure of the Fisher-Gray model. Remember, what we're trying to do with this is to talk about expectations and where they come from and how they interact with our policy choices. So if we change our policy, we can say something about how expectations of wage setters are going to change as well, right? So, and in a larger sense, we're trying to get an idea how modern macroeconomics is done. Right? So here's what we've gotten so far. We've gotten equation 6, which is yt minus y bar equals theta pt minus pt given t minus 1. Can you see it? Yes, you can see it. How lovely. I believe I am recording this, so it will go into the slides, and I will certainly scan these and put these on the web. So, take notes accordingly. I'll definitely scan them and put them there. Hopefully, we'll have a video of it as well. Okay, so we have that, which is something about the goods market, how it depends on price prediction errors. Right? They're predicting the prices, today's prices, one period ago when they were setting their wages. And if they guess the price is too low, then output is high, right? Because they guess the price is low, so they set low wages. And then when the prices are high, the output price of the goods are high, and firms find it very cheap to hire us in real terms, and they hire lots of us, right? And if price prediction errors are too high, then output is low. Because we set our wages really high, but prices weren't that high, and so firms want to hire fewer of them, right? The prices are what the firms are getting for their product, but the wages are what they're paying the people to make them. Right. So that was the goods market. And then we had 7, which is the money market. MT minus PT is equal to YT minus Y bar minus VT, where VT is velocity. Right? It's how quickly money goes around. M is the amount of money in the economy. P, of course, is the price level, and so on. This thing does not want to stick on me today. We will do our best. Okay, so that's our goods market. That's our money market. Those are the two main equilibrium in the model. And as we go forward, this will be how I will present the model to you. I'll do variations on this model, but we won't derive everything about that variation. We'll just jump right to these equations and modifications of these equations. Okay, so these are our two main equilibrium equations, but it's important that you see it the first time so that you can say, okay, that's where it comes from. Here's how we're taking logs of things. All these small letters are natural logs of the various values, and so forth. So you can see the whole infrastructure. You know what it went into the model. Okay. Nothing much went into the model that wasn't in our Phillips curve model. It's basically the same model. We're talking about prices instead of inflation, but otherwise it's the same thing going on. Okay. We've just translated it into math. Okay. And we said last time that we've got more variables here than we've got equations. We only have 2 equations, and we want to know what output is. We want to know what prices are. We want to know what the money supply is. We want to know what the velocity is. And we want to know these expectations. So we've got to add something to the model. We don't have enough to solve it because we only have 2 equations, but we've got 4 or 5 things that we want to learn about. And so we have to either add more equilibrium conditions so we have more information going in, or we have to say, I don't want to learn about that thing. That's fine. We'll take it as outside the model and understand it accordingly. So a couple of things that we're going to do is we are going to say Vt is random. And this is because we need to really talk about expectations. So far, we've had these perfectly deterministic models where everything is known. Everything is known in the economy. Everything is known by everybody. There's no reason why anyone will ever make a mistake in a model like that. But in real life, people do make mistakes. In real life, prediction is difficult, especially about the future. Yogi Berra. It's a difficult problem to figure out what's going to happen in the future, and we're always going to get it wrong a bit, right? And so we need something unpredictable in our model to really be talking about expectations in any kind of interesting way. Okay? And there's lots of things that could be unpredictable in real life. There could be unpredictable demand, there could be weather, there could be all sorts of things that are unpredictable in real life. But the easiest way to get it into our model is in this velocity term. It's not that we really think that changes in how quickly people spend money drive everything in the economy, but it's the easiest way for us to bring randomness into this model. Because they're just sort of sticking out there. We don't really have any stories about velocity so far, so we can make it random, and it's fine. Okay? Now, we're going to do this, and we're going to make velocity random the whole time, but we could do more sophisticated sources of randomness, and all these same stories that we're going to tell are fundamentally true. You get interesting stuff out of that, but not these stories about expectations that we're going to tell here. So we just put it in the simplest possible way, and something unpredictable, and that is to stick it in as velocity. So sometimes people spend their money very quickly. Sometimes they spend it very slowly. Sometimes velocity is high. Sometimes it's low. And we are going to assume it's random in a particular way. Vt is going to be equal to epsilon t, which is going to be IID mean zero. Let's see. Identically, what is the I? Independently and identically distributed. So these shocks, this is going to be our shock term, our random term, this epsilon, and that's going to be v. We're going to specify v in different ways in other versions of this model. So I want to keep it as v as random, and then specify how v is the nature of its randomness. Here, every year, every period, there's this new velocity shock that comes from some random distribution. Sometimes it's high, sometimes it's low. Right? And each time, it's independent of the last time. So if last year's was high, that tells you nothing about this year. There's no connection between this year's velocity and last year's velocity. Okay. We're gonna change that later on, right? But for the moment, they're independently distributed. There's no knowing today's velocity tells you absolutely nothing about tomorrow's velocity, and they're identically distributed, so the randomness that velocity came from this period is the same as the randomness that it's going to come from next period. Now, they're coming from the same distribution each period, and there's no connection between the periods. Okay? And just to make our life easy, we're going to say that on average, there's zero. Okay? We could have some other average. We just have a constant floating around that wouldn't change anything for us. Mean zero is the easiest. That, of course, does not mean that velocity itself is zero, because remember, this is the log of velocity. So that means that on average, velocity is 1, or actually velocity divided by the potential output is 1, which is some number, right? Because log of 1 is equal to 0. And so if our little v is on average 0, that means on average, our velocity euros get spent once per year, or once per period, whatever the length of the period is. Okay? So that's going to be our source of randomness. This is the simplest one we can come up with to start ourselves off, but we're going to make it more interesting as we go along. Okay? But we'll start out simple. All right. And the other thing we're going to do, so that gets rid of our velocity. We've dealt with that. We don't have to solve for that. The other thing we're going to do is this m, because m is a policy variable. Right? This is something that the central bank can just pick. And so we're going to ask the question, how should they pick it? Should they pick it high? Should they pick it low? And so we're not going to explain it. We're just going to see, given what the money supply is, what's going to happen in this economy. So this is something that we're not going to try to explain. We're going to try to use as a policy tool. Okay? So that leaves us with what? YT, PT, and kinda PT given t minus 1 left to explain. I say kind of PT given t minus 1 because it's clearly in some sense related to PT itself. We just haven't specified the sense yet. Okay, so we've got 3 things that we need to explain now because we've dealt with this velocity. Okay, we've said it's random. And we dealt with the M. We said we're not going to try to explain it. That's outside the model. It's something that we're using to control stuff. And so we have these 3 things left to explain, but we only got the 2 equations. So we need to do something, right? With 2 equations, you can't explain 3 things. We need something else in this model to explain, to get things going, right? And you cannot see what I wrote. Fun times. Okay. So what we're going to do is we are going to assume a process for how expectations are formed, right? People have to, if we can get everything in at once would be beautiful. What do we zoom out? Zooming out, is that a thing? Oh, zooming out. Yes, we can get more in. Zoom out. Okay, that's maximum out. So we have this price prediction error. It really depends on how this expectation is formed. This is last year. They're trying to guess what the prices are going to be this year so that they can form their wages. How do they go about doing that? And our initial pass is going to be adaptive expectations. We're going to have adaptive expectations, which means people are backward looking. That is, they use their current state of the world and maybe possibly the state of the world now and in the past, but they're not like sophisticated looking forward. They're saying the world is going to be either like it is today or following some trend that we had from the past, but they don't say, is that trend likely to last under what conditions? They just say, take the past and in some mechanistic way predict the future from that. Okay? We're going to take the very simplest form of adaptive expectations, and that is we're going to say that PT given t minus 1 is just PT minus 1. That people think tomorrow is just like today. So at t minus 1, when they're forming their expectations, they think prices are just going to be the same. Okay? We could have more sophisticated versions where they have some kind of moving average of prices in the past 5 periods or whatever. We would get fundamentally the same conclusions, but things would be messier, and we don't need that. This is your first time doing this stuff. Why are we making it messy? We want to make it as simple as possible. So that's going to be our story about expectations. So now we've got these 3 things we want to explain, PT minus 1, and Y. And now we've got 3 equations, right? We've got 6, 7, and this little thing. Now we got PT minus 1, which is a little weird, but these 2 equations are actually 2 equations at time t. There's similar equations for the period before, and similar equations for the period before that, right? For any particular choice of time, there's a set of equilibrium conditions that look like that. So we think we've got 2, but really we have an infinite set of time. Each time period has 2 equations that look like that. So we have as many as there is time. So we've covered the bases. Now we just have to solve this thing. Okay. And to solve this thing, what I want to do is, I'm not going to fit anything on this page. I'm going to copy this stuff again. 6yt minus y bar is equal to theta pt minus pt given t minus 1.
7 is mt minus pt equals yt minus y bar minus bt. And we got pt given t minus 1 is equal to pt minus 1. And that's our situation. And we want to solve this thing. We want to find out what's going on. And our fundamental trouble is this first equation, equation 6, right, where we've got this price prediction error. So this is a model all about price prediction errors. Output goes high or low based on price prediction errors. And so we want to say something about those price prediction errors. We want to write everything in terms of price prediction errors. I can struggle with technology as per usual. And so what I'm going to do is I'm going to take 6 and I'm going to plug it into 7. Remember, now that we have it in equation form, we can do anything legal in terms of math and we're fine. So if we want to plug one equation into each other, why not? Go crazy out there. It's fine. If you want to divide everything by 57,000, go for it. It's fine. Okay? Some is useful, some is not, but any legal math thing, we're good to go. And so I want to simplify this, and we have 2 equations, 2 unknowns. What we do is we take one equation, we plug it into the other. That helps us get rid of it. And by doing that, I can get rid of y, right? As I plug that in, I've got one less thing to worry about. So what I'm going to do is I'm going to take this bit here and plug it in for that bit there. Okay. And one way you can think of this, that's a mechanical way to think about that, and that's not wrong. Another way to think about this is that we're really interested in prices, right? Because everything is being driven by these price prediction errors. And prices are in a sense, a feature of the monetary side of the economy. Right? It's really going to depend on money supply in some way, what prices are. And so what we want to do is we want to look at that financial side of the economy where nominal values come from. Right? Real stuff, like how many tractors we make, comes from the goods side. But what things cost on average comes really from the money side. So I want to reduce all this into a money equation so that I can look at these price prediction errors. Okay? Now, mechanically, we could plug the lower one into the upper one. It would be the same thing, right? It's algebraically the same. But in terms of story, thinking of it in terms of we want to look at the financial markets here because the price level is a financial sort of thing, right? So I'm going to plug that in. I'm going to write 7 prime. 7 prime is going to be mt minus pt is equal to yt minus y bar, which is just theta pt minus pt given t minus 1 minus vt. Right. Just plug that in. And then I got this expectation term, which is just a pain. Right? It's like, as soon as we saw that, we knew that was going to be trouble. But we can get rid of it because we have these adaptive expectations. Is that what I want to do? Actually, I don't think that's what I want to do. We could do that. Yeah, let me leave that way, actually. I was going to plug this in, but that's not actually helpful. What I'm going to do instead, I could do that, right? I could just plug that in. That would be fine. It would be kosher, no troubles. But in fact, what I want to do is take this one period earlier. So the same equation, just one period before, because this equation has to hold every single period. Every year, it's a brand new year. This is what equilibrium looks like in this economy, right? So it looks like that in time t. It also looks similarly in time t minus 1. Okay, so we get mt minus 1 minus pt minus 1 equals theta pt minus 1 minus pt minus 1 given t minus 2 information minus vt minus 1. Okay. So now, what did I do here? Okay, I see what I did. Following my own notes. It's so hard. It's so hard. Should I just go for it? No, I shouldn't. I'm going to cross that off. Oh, the bastard, the bastard. It's not wrong. It is not wrong. But this pt minus 2 is going to cause us nightmares. So I'm going to slink away in embarrassment and shame. Oh, this is it. This is when they all come and kill me, and I need to run for the exit. Yeah, rather than dig myself a deeper hole, I am going to step back and actually follow my notes, which will be new and exciting. Okay. Okay, so what do we got? We've got this one, 7 prime is fine. Prime, so we get mt minus pt is equal to theta pt minus pt given t minus 1. Is it? Nope. Okay. I want to play around with 7 first. That's the deal. Yeah. So I'm going to play around with 7 first. That's all true. That's all true, but not helpful. That's the way we do it with the rational expectations. Sorry. Okay. Okay, I'm on track. Am I? I've lost that. Nobody has any faith in me anymore. What a goofy job. Okay. Doing algebra in public. Oh, can you believe it? Okay. So I want to solve this since we're wondering about prices, right? Okay. Now we're on track. We're wondering about these price prediction errors. So we really want to know, where do prices come from in this model? Right? So and we're thinking it come from the money market. So I'm going to take this money market and I'm going to solve for prices because that's where prices come from. Right? I want to find out what do prices look like in this model. And so solving this per prices, equation 7 becomes pt equals mt plus vt minus yt minus y bar. Right? And, okay, now I could do that. That's where prices come from in period t. And we're wondering what were things last period. So let's put in last period as well. So that's 1 period earlier. We get pt minus 1 is equal to mt minus 1 plus vt minus 1 minus yt minus 1 minus y bar, which we can do. Everything's good, right? Okay. Now, what I'm going to do is I'm going to wonder, how did prices change? So I'm going to take the first one and I'm going to subtract the second one. So take that first line and subtract the second line. So I get pt minus pt minus 1, taking this and subtracting that. Right? And you can see already why that might be of some interest, right? Because where we're trying to go is this phrase, pt given our expectation at t minus 1, pt minus t minus 1 seems quite closely related to that. Right, so this difference in prices, how did prices change over time? And that's equal to mt minus 1, like so. plus vt minus vt minus 1 minus yt minus yt minus 1. Actually, how do I want to write that? Let me actually just write it out. Minus yt minus y bar plus yt minus 1 minus y bar. Right, because we have this one, which is positive, then we're subtracting this negative thing, so that turns it into a plus. Okay. There we go. You would not believe, but I actually did spend an hour before class going over these. How hard could it be? Okay. Okay. Now, let's look at 6. Six is up here, right? But we know what pt given t minus 1 is. It's this, right? So we can rewrite 6 as yt minus y bar is equal to theta pt minus pt given t minus 1. Not given t minus, just pt, minus pt minus 1. Some people should not be allowed to do algebra. There should be a law, right? Right, because if we look at 6, that was price prediction errors, and we were always wondering, what is this expectation term? Well, given our adaptive expectations assumption is just yesterday's prices. So output is going to be theta times the difference in our prices today and yesterday and today, right? So we've got that here, and we've got that here, right? So this was manipulating 7, right, using last period and this period. And this is just using 6 and the adaptive expectations assumption. Right? So now we can plug all of this mess into here. So we get yt minus y bar is equal to theta times all of this stuff on the right-hand side. Now we're on track. Honest, we are. I know, I've lost all credibility. So let me plug that in. We get yt minus y bar is equal to theta times everything on the right-hand side of that other equation, which is mt minus 1 plus vt minus vt minus 1 plus minus yt minus y bar plus yt minus 1 minus y bar. Like so. And then end bracket. Okay. And now I can solve for output. Right, so I've got today's output here, and I've got today's output there. So I've got minus theta. I have one of these here. And on this side, I've got minus theta of them. Right? This theta times that minus. So if I take all that over on the left-hand side, I get 1 plus theta yt minus y bar is equal to theta mt minus 1 plus vt minus 1 plus yt minus 1 minus y bar, like so. And of course, now we can solve that. Solve for output. We get yt minus y bar is equal to theta over 1 plus theta, all the bracketed stuff. Right, all this stuff. And this is our adaptive expectation solution. Yay, team, we did it. Well, you put up with it, and it got done eventually. All right. So, did we learn anything? We learned that algebra is a pain to do in public. Don't do it. It also learned that it's probably a pain to do on an exam situation, so be prepared. You will not have to do this adaptive expectation stuff on an exam situation, by the way. The stuff we're going to do, not quite next, but after that is what you'll have to do, which is actually easier, like genuinely easier, but less error prone. Let me put it that way. Okay? But have we learned anything? Well, in fact, we did. Right? We learned that monetary policy is effective. With these adaptive expectations, we are able to change output. Right? Because you see, MT is right there. If we want output higher, we increase the money supply. Right? What does that do? Well, people have already set their prices, right? They've already set their wages. If I increase the money supply, I drive up prices. That makes it so that firms are selling stuff at a high price, but the wages are still low, so they hire workers, produce more stuff. And I can do that, no troubles. Yeah? Uh-huh.
So we have yt minus y bar.
Uh-huh.
Represent the output production.
Yes.
And in the money market, it's actually the same value,
Uh-huh.
but represent the consumption.
Yes. Yes. So
You're equal, when you produce that doesn't so we have to consume exactly the same amount.
yeah.
We
Yeah. This is a very good question, so let me repeat it. This is insightful. So let's go back to equations 6 and 7. Here on equations 6 and 7. Now let me go to a neat version that I haven't scribbled all over. Here we go, 6 and 7. Right? The top equation is representing the goods market, and it's got y minus y bar in there. Right? That's saying how much is output. Saying how much is output depending on these price prediction errors. Right? And the other equation is representing the money market, and that also has yt minus y bar in there. Right? And we could think about it the other way. The top one has prices in there. Even though it's the goods market, it has prices in there. But we're thinking prices are coming from the money market, so prices are in both of them. Right? And this is a general thing in economics. Right? In general, in economics, everything is interrelated. Everything affects everything. You cannot just isolate the goods market and it's unrelated to the money market. Sometimes under special assumptions, but those aren't the interesting cases, right? The reason we're doing all this studying of the thing is because everything is interrelated and we have to disentangle them. And this equation is saying everything is interrelated, right? Because these price prediction errors determined output. but it also determines demand for money, right? How much product has to be bought. And so that's going to affect the prices. If we're buying lots and lots of stuff and we only have so much money, the price has got to be lower if velocity is given, right? So it's determining both at the same time. And notionally in our heads, we're kind of thinking, yeah, output is determined in the good market. And notionally in our heads, we have prices are determined in the money markets. But in fact, it's all jointly determined. Right? And the equation is telling us that. Everything affects everything else, and they're all jointly determined. Right? The way we're simplifying things by making the model is sort of a way of organizing our thoughts about this complicated, interrelated thing. Right? So we're sort of thinking of them as separate things, but of course, in the end, they're not. Right? Which is why we combine the equation. Right? We're making them both true at the same time. So it is really just notional that it's on one side or the other, just to organize our brains, but in reality, it's on both, right?
Because we try to predict the year or predict it to the prices.
Uh-huh.
And then if the consumption, say, we have inflation, that will give extra money to the producer, but the consumer will get less.
Yeah.
So that's double the year.
Yeah, we don't have the consumer versus producer distinction in this particular model yet, but yeah, like if output is high and money supply is right, like keep M and V the same. If output is high, prices have to be lower, right? Because there's only so much money. It's only going around twice in a year. So we're buying more stuff. It's got to be that the price is lower. Right? No? Yeah, not really, but kind of vaguely. Okay. Okay. So monetary policy can change output. How is it doing this? Well, people aren't really trying to predict monetary policy, right? They just said, okay, our prices next year are just going to be just like our prices this year. So there's no notion of them thinking, what is the central bank going to do? Is it going to try to increase prices? And if it does, maybe I should take that into account in my expected prices. There's nothing like that. They're completely adaptive expectations. They're just backward looking. And so this notion that the central bank might surprise them isn't there. And so if central bank wants to increase output, right, it raises the money supply. By raising the money supply, it's raising prices. So what it's doing is it's tricking consumers. It's tricking workers, right? They set their wage based on one set of expected prices, today's prices, and then the money supply goes up, prices go up, and they can buy less stuff than they could before. So firms are finding them cheap, they're finding life expensive. So money supply can affect output by systematically tricking the consumer, right? By tricking the worker. Another thing we get from this, is that business cycles will be persistent. Suppose we did nothing. We did absolutely nothing with the money supply. We kept it the same each and every time. So that first term, that MT minus 1, just stays constant. That's just zero, right? We keep money supply the same every time. And suppose that just by random chance, today's velocity is just like yesterday's velocity, right? Or close enough, right? Well, output will be theta over 1 minus theta times last year's output differential. So a fraction of last year's output differential. So this shock, so if there was a shock 2 periods ago, and then no shocks afterwards, so output got really high 2 periods ago, that's going to stick around period after period. If we do nothing and there's no other shocks, it's going to slowly die out, but it's going to take a while. And this is interesting because all of our shocks, all the randomness in this model is just IID, right? It's idiosyncratic. It comes, today's shock unrelated to yesterday's shock. But if there's a big shock, let's say there's a big recession, there's a big negative shock, then we have output is low. that's going to stick around for a while, even though there's nothing in the shock that says it does, right? Okay. Those are our two big conclusions from this model. And the third big conclusion is this is not a good way to do expectations, right? Because monetary policy is changing output by tricking people. And we're right back, and it shouldn't be a surprise that we're right back in the Phillips curve story, right? As long as you're not playing around with monetary policy, everything is stable. But as soon as you start playing around with monetary policy, you're systematically tricking people. And if you're trying to keep output high, you're increasing the money supply every year. Prices are going up every year. Eventually, people are going to cop on, right? They're going to say, hey, this is not right. Right? And they're kind of copping on, right? They're saying prices are going to be just like today. And the next time, prices are going to be just like today. Prices are going to be just like today. So they are raising their expected prices, but they're never anticipating what the central bank is doing, right? So we have a model that has people systematically being tricked. And for a long time, like empirical stuff, like policy stuff, was done based on adaptive expectations like this. And truth be told, sophisticated versions of adaptive expectations are actually not unreasonable for policy. Like, they can match what people seem to do pretty well. But if we want to have big changes in policy, it's unclear how people's expectations would change, right? Maybe there are adaptive expectations at the moment, but if we start doing wild swings in policy, they're going to be more sophisticated. They're going to try to predict those swings. And so the literature has moved on to another extreme. So this is a very extreme case where workers and firms are just thinking tomorrow is like today. Okay? Our other extreme is that workers and firms are going to be extremely sophisticated as a professional economist. And they're going to know everything that we know about the economy. And these equations are the economy, so everyone in the model is going to know these equations too. And importantly, they're going to be actively trying to predict what the monetary policy is. Right? And so the way we set monetary policy will affect how they form their expectations as well. Okay? And this is rational expectations. It's another extreme where everyone is extremely sophisticated about the model. The model is real. They take all that information into account. And real life, I'm thinking, I don't know if any economists agree with me, but I'm thinking real life is kind of in between. Like sometimes people are, they spend a lot of effort trying to predict policymakers, but other times, tomorrow's more or less like today, or we draw a line and we extend the line. But you can be the judge of that. But from a theoretician's point of view, rational expectations are really important. So from a policy point of view, they're important, particularly when we're making big policy changes. But from a theoretical point of view, they're extremely important because if you have adaptive expectations, I can set up those adaptive expectations in a way to get kind of any answer I want. Right? So if I want to show that monetary policy is great, I set up my adaptive expectations accordingly. If I want to show that it's terrible, I set up my adaptive expectations because I'm just saying, you guys have to expect this, right? And I can since expectations are so important for the economy, if I'm just imposing them on the model, I can get whatever result I want, right? And so we are going to look for expectations where people are not being systematically tricked. They're going to get it wrong sometimes, but not in a systematic way. Okay? And that's going to be rational expectations, which is going to be the theme for next time, a time when there will be no algebra errors. It'll be glorious. Glorious. Okay, I'll see you on Friday.